Hello mathematicians. Today we see a nice real analysis problem asked in the Nbhm PhD 2020 exam. Let x be the space of all real polynomials of degree at most 5. Degree at most 5 means that there will be a constant term and there will be coefficient of t up to coefficient of t power 5. There will be 6 coefficients. So we may think of X as a topological space via its identification with r power 6. There are 6 coefficients, so we are identifying it as r power 6. Now, which of the following subset of X is connected? So you take X and you look at r power 6. R power 6 has usual topology induced from the usual metric. You consider the same topology in X also. They are asking which of the spaces are connected and disconnected, connected or disconnected. Consider the polynomials that do not vanish at t equal to 2, whose derivatives vanishes at t equal to 3, vanishes at both t equal to 4 and 5, all polynomials in x which are increasing. We want to say which of these sets are connected or disconnected. Let's see. Let's look at the first option. So set of all so for the first option it is given that set of all polynomials which do not vanish at t equal to 2. We define a map phi from the set A to R by pi of a polynomial p of x is equal to p of 2. So this is called evaluation map, evaluating at the point 2. Okay. So why it is a continuous function? First of all, so for the time being, let's assume it is continuous and let's argue. So you if since p of x consists of polynomials which do not vanish at the point p of 2, which do not vanish at the point 2, we can prove that the range of this function will be minus infinity to comma open interval minus infinity comma 0 to 0 to plus infinity. Okay, so it is like suppose if you take a element alpha belongs to r star, then you can consider p of x equal to x minus 2 plus alpha. Okay, then p of alpha will be alpha. Sorry, then p of 2 will be alpha. Therefore, given a point here, you can find a polynomial. Note that p of 2 is not equal to 0. There is a polynomial here whose image will be alpha. Therefore, range of this function is my r star, non-zero real numbers. So we conclude that if we assume that this map phi is continuous, range is disconnected, therefore domain cannot be connected. Okay. Now why this evaluation map evaluating at 2 is continuous? Let's see. So suppose for the time being assume that p of x is equal to this polynomial a power 5, a5 t power 5, a4 t power 4 plus etc. This is the polynomial, and so we are sending this polynomial to p of 2. So that will be a power 5 times 2 power 5 plus a power 4 times 2 power 4 plus etc. plus a1 times 2 plus the constant term a naught. Okay. Now this polynomial goes to the leading coefficient. Just this polynomial goes to a5. That is a continuous function because that is the projection onto the uh, this is a projection like how we are identifying. So we are identifying these polynomials with r power 6 this way. So this polynomial goes to a power 5 is same as this tuple goes to a power 5. That is precisely projection onto first coordinate. So therefore this polynomial goes to a power 5 is a continuous function because it is projection. Similarly, the polynomial, if you map this polynomial to other coefficient, that is also continuous function. So now like look at this t power 5, t power 4, t cube, t square, t, they are all polynomials, right? So maybe this I should put the p of t. Okay, and we are evaluating 2 at those polynomials, right? So they will also continuous. So this projection to coordinates also continuous, and you are evaluating at this polynomial is also continuous. Therefore, overall evaluating the value 2 at this polynomial is a product of various continuous functions. Therefore, phi is a continuous function, that evaluating at 2 is a continuous function. Therefore, A is disconnected is proved. Okay, so it is disconnected. So very much remaining options also similar only. So let's look at polynomials whose derivative when is at t equal to 3. So set of all polynomials such that p prime of 3 equal to 0. So now we claim that this space is path connected. Path connected means you takes 2 points here, and then there is a path joining them. Okay, that means that like so suppose you have a point A and you have a point B, then the line segment joining A and B, we claim that this line segment joining A and B will belongs to B if both these points are belongs to B. Okay, but what is the, how to what is the parameterization of the line joining A and B? That is given by TA plus 1 minus T times B. Okay, so 0 less than or equal to T less than or equal to 1. So as T varies from 0 to 1, you get the line segment joining A to B. Okay, so similarly here we also argue, so we take two elements. So if P and Q belongs to B, then they are polynomials who evaluated at whose derivative evaluated at 3 will be 0. Now I fix 0 less than or equal to T less than or equal to 1, and I look at I claim that this TP plus 1 minus TQ will be again an element of this set. So to prove that some polynomial is an element of the set, you have to prove that its derivative evaluated at 3 equal to 0. So we calculate its derivative and we evaluate its derivative at the point 3. Okay. So now this t and 1 minus t are scalars, right? Real numbers, in particular scalars. So this will give us t times p prime of 3 plus 1 minus t times q prime of 3. Okay, so I think there is a slight confusion because they are giving the variables t, but I am taking variables x. That is why this I so this t's are scalars. Okay, for them t's are not scalars. For them t is variables, but I am taking variables as x, polynomials in x. I hope that is fine. Okay, so now this is t times p prime of 3 plus 1 minus t times q prime of 3 by definition. So this is 0, this is 0, so overall we get 0. Therefore, this tp plus 1 minus tq also has derivative which is evaluated at 3 is 0. Therefore, given any 2 points here, the line joining those 2 points also belongs to B. Therefore, B is path connected. Okay, let's come to C. So set of all polynomials when is set both 4 and 5, that is option C. When is set both 4 and 5. So now by you, let's consider C1, set of all polynomials vanishing at 4, set of all polynomials vanish at 5. Now again you can prove that these two spaces are path connected like the same argument. Okay, so therefore this is path connected, this is path connected, and if you take union of, sorry, not union, you should take the intersection. So if you take the intersection of them, so here the polynomials vanish at 4, here polynomials vanish at 5. If you take the intersection, the polynomials will vanish at 4, vanish at um, both 4 and 5. Now this is connected, path connected implies connected. Okay, so connected, this is connected, and intersection of two connected space is connected if they have non-empty intersection. Now these two intersection of these two spaces is non-empty, because if you look at the polynomial x minus 4 into x minus 5, it is a polynomial of degree at most 5, but this polynomial belongs to both c1 and c2. Okay, therefore these two are connected sets whose intersection is non-empty. Therefore, intersection is also connected. So we get C is the set, give this set is connected. Okay. So let's move on to the fourth option. All polynomials in X that are increasing. So set of you consider increasing polynomials. We claim that again that is also connected. So again you take two polynomials and we claim that the line joining these two polynomials, this t times p plus 1 minus t times q also increasing. If p and q are increasing, we claim that uh, tp plus 1 minus t q, that new polynomial is also increasing. Note that t is coefficient is this t are scalars. We are taking the variable is x. Okay. Now to prove this function tp plus 1 minus tq is increasing, I claim that suppose I assume x1 less than x2. I want to show that tp plus 1 minus t times q of x1 less than or equal to tp plus 1 minus t cube is of x2. Okay, this will imply that this function is increasing. So let's see. So x1 x less than x2 implies since p and q are increasing, we get these two inequalities. Now we can, in this inequality, we can both side multiply with t because t is non-negative. Again both the sides, here we can multiply both side by 1 minus t because again 1 minus t is non-negative. We can add the inequalities, there is no problem. You are adding smaller number with smaller number and bigger number with bigger number, so the inequality is preserved. Okay, this precisely means that Tp plus 1 minus Tq of x1 less than or equal to Tp plus 1 minus Tq of x2. Therefore, if P and Q are increasing, their linear combination Tp plus 1 minus 2Q also increasing. Therefore, this set is path connected. Okay. Okay. I hope you understand something new in this problem. So I just connected. Okay, so if you learned something new from this video, please click the like button and share with your friends and subscribe to my channel. Thank you.